Hey there, Hassler. Going to give you some notes on 6.2. We are going to be approximating and finding the area under a curve. If you recall, we talked about area under a curve meaning the space between a function and the x-axis. When we were finding area before, we were able to use geometry shapes to find exact area. But what happens if I have a curve like a parabola or some other function where I cannot use geometry shapes? There has to be a way in which we can best estimate the area under that curve. And there are a couple ways we can do that. So one way we can do that is to use something called a Riemann sum. And a Riemann sum was named after a mathematician, Riemann. And it is a way to approximate area under a curve. With Riemann sums, we are using rectangles, and either one of the corners of the rectangle will be a point on your curve or your function, or the center of the top of the rectangle will be on the curve. So we'll do some examples of that. A single rectangle is called a subinterval. A subinterval would be a smaller interval of a large interval. So if I have the function f of x on an interval a to b, I can approximate the area under that curve using n subintervals, okay? Now, in order to determine how wide those subintervals are, we are going to call that delta x. Delta x would be the width of the subinterval, and that is equal to the length of my interval. In other words, sorry, I'm just trying to delete this. There we go. In other words, I'm going to have b minus a, the distance between my x values, divided by n, the number of subintervals that I'm going to have. And so I'll show you how that works. I want to come back to trapezoidal sum. I just want to do a couple Riemann sum examples, okay? So below is the graph of the function 4x minus 1/2 x squared. We're going to use different Riemann sums in order to approximate the area under this curve on the given subinterval, or sorry, using subintervals of equal length. This is going to be important, okay? Not all subintervals have to have the same width unless specified. So if it says of equal length, then every subinterval will be the same width. All right, so a left Riemann sum is that the left upper corner of the rectangle that we draw, okay, will be on the curve. All right, the left upper corner of the rectangle will be on the curve. So the first thing I have to do is I have to say, well, I'm going to start drawing rectangles here when x is 2, and I'm going to stop drawing rectangles when x is 8. But I have to know how to draw those rectangles. 3 subintervals means I'm going to draw 3 rectangles, and I want them to be of equal length. And so what that means is I've got to figure out how wide each rectangle is. That's the delta x. And so that's the length of my large interval, 8 minus 2, divided by how many subintervals I need, 3. And so 6 divided by 3 is 2. That means that each rectangle I draw should have a base width of 2. All right, so I'm going to go and draw these rectangles. The other thing I need to know is where to put the corner of my rectangle. It says left upper corner for a left Riemann sum. What that means is if I split this number line into 3 equal subintervals, right, every 2 units, so each rectangle is going to have a base width of 2. I have 3 rectangles that are going to be drawn. I'm going to start on the leftmost rectangle, and I'm going to draw that rectangle so that the left corner of that rectangle is touching my curve. And I'm going to flatten out that top edge, and then I'm going to come back down and end here at 4 since each rectangle has a width of 2. Okay. All right, I'm going to do the same thing again. Get a different color in here. I'm going to start at my next subinterval, and I'm going to draw so that the left corner of that rectangle is touching my curve. And I'm going to finish out that rectangle, oops, so that it has a width of 2. Okay. Oops. There we go. All right. If you want, you can feel free to color these in. All right, same idea. For this next rectangle, this next subinterval, I'm going to start on the left side until that left corner is touching my curve. I'm going to finish drawing out that rectangle. And what you notice is that on this interval from 2 to 8, I have a lot of extra area that is not under my curve. So right here, I got extra area. Right here, I have extra area. But I also have area under my curve that doesn't get calculated, okay? So it doesn't feel like it's that great of an approximation, and we'll talk a little bit more about how to get a better approximation. But for right now, we just want to practice doing our calculations, okay? And so if I want to find the area, I'm going to have to say, well, base times height, right? Area of a rectangle is base times height. And the base of each of these rectangles is 2. So base is 2 times, well, my first rectangle has a height of, looks like 6. But the way I'm going to write it is that it has a height of f of 2. In other words, if I evaluate my f function, this right here, if I evaluate the f function at 2, whatever the output is going to be the height. Now I know I can easily see that that is 6, but I simply want to bring this up to you because it won't always be easy to see, or you might not always have a graph. Okay, plus now I have to calculate the area of this second rectangle. So again, width of 2 times, and in order to get the height of that rectangle, I have to evaluate my function at 4, because 4 is the x value that matches that left corner. And plus base of 2 times f of, well, this corner right here goes with an x value of 6, so f of 6. Again, I really have 2 times 6 plus 2 times 8 plus 2 times 6. And if I do that calculation, I would get 40. Okay, so the area under my curve on the interval 2 to 8 looks to be about 40. But again, we know that's not exact because I have some overage and I have some underestimating. The question will become, how can I get the best approximation? Okay. All right, let's try a right Riemann sum. And you guessed it, a right Riemann sum, I'll go pink this time. A right Riemann sum is where I put the right upper corner of my rectangle on the curve. So again, I'm still using the interval 2 to 8. I still have 3 equal subintervals. And so if I want to calculate what that would be, I would have, again, delta x would be the same thing, right? 8 minus 2, yikes. 8 minus 2 divided by 3. And so that's going to give me width of 2. So I'm going to come down here, 2, width of 2, so it gives me 4, 6, and 8. But this time it's going to be the right upper corner that's going to be on my rectangle. So when I look at this subinterval here, this first rectangle, instead of starting at 2, I'm going to start over here on the right side of this rectangle at 4. And that's the one I'm going to draw up to my curve. And then I'm going to move over to finish my rectangle. Okay. All right. Same idea here. I'm going to look at my next subinterval, and I'm going to start on the right side since I'm doing a right Riemann sum. And I'm going to go up until I touch my curve, and I'm going to move over to the left there to finish my rectangle. Now this is where things get interesting because what happens is when I go to draw my rectangle and I start here at the right side's at 0. And so I have no rectangle because I have no height. There's no rectangle there. And so again, maybe not the best approximation because I have lots of space that is not accounted for. And I have this time actually a very little amount of space that is extra above. So again, we'll talk about how to get a better approximation, but for now, we're just practicing. And so if I want to find the area, that is equal to 2, that's the width of my base here, times the height. But see, this time the height is calculated by doing f of 4, because 4 is the right x value of that subinterval. Okay, plus 2 times, well, this time it's going to be an x value of 6. So f of 6 plus 2 times, well, f of 8. And again, because this graph is easy to see what those outputs are, I can just say, well, 2 times 8 plus 2 times 6 plus, well, 2 times 0. When I calculate this, I get 28. And so notice that I am working on the same interval, 2 to 8, the same interval in both cases, 2 to 8. And I have the same number of rectangles. But one area formula is giving me 40, meaning that the area under that curve between 2 to 8 is 40 units squared, versus same interval, but this time I'm getting an area of 28. Okay, so, and obviously we can see that there's an overage or an underestimation. So what happens if we meet in the middle? And that is what a midpoint Riemann sum is going to do. Okay, can we balance this out? All right. And so a midpoint Riemann sum occurs when the midpoint, go figure, or the center, we can say, of the top edge of rectangle, okay, is on the curve. All right. Okay. So again, I could still figure out what delta x is. I still am on the interval 2 to 8. I still have 3 subintervals, so delta x is still going to be 2. Starting at 2, a width of 2 gets me to 4, to 6, to 8. But this time it's the center of the top edge of that rectangle that's touching my curve, okay? And so what that means is that I need to locate the center of this subinterval, and the center of this subinterval is 3. And so what I'm going to do is I'm going to go up and I'm going to look at the point on the curve when that middle x value, in this case, is 3. And then I'm going to draw my rectangle so that I still have a width of 2. It's just that the center of that rectangle is what's on the curve. And you can see I got a little bit of under, but I got a little bit of over. So it kind of balances things out a little bit. Okay, so let's do the next one. Again, I got to look at the center of this subinterval from 4 to 6, and the x that's in the center is 5. So I'm going to go up to 5 on my curve, and then I'm going to draw my rectangle so that it's going through that point of my curve at the center, which is at an x value of 5. And again, we get a little overage and a little under, so it feels a little bit more balanced. Okay. And finally, I have to look at the midpoint of this subinterval, which is 7. So I'm going to use the x value of 7. and that's going to be on my curve. And then I'm going to draw my rectangle. And I got to find the area of that. Okay. All right, so let me set up my area formula for this. It looks like my area formula is still base 2 times, well, this time I have to evaluate f of 3 because 3 is the midpoint of my x from 2 to 4, my subinterval, plus base of 2 times, okay, so that was 3, all right, the height of my function at an x value of 5 plus 2 times the height of my function when x is 7. So this isn't as easy to tell, and I'm not going to estimate just to estimate. And so what I can do is I can use my calculator. And so I want you guys to go grab that. I don't have access to my graphing calculator on this program or computer, but what you can do is you can go to your y equals. This original function, remember, is f of x equals 4x minus 1/2 x squared. So type that into y1, okay? And then, of course, go to your table. And while you're in your table, you're going to type in these x values of 3. Oops, what's happening? There we go. Of 3, 5, and 7, so you can get the outputs that go with it. And then you can calculate that. So I really have 2. We could have estimated, but we wanted to be sure, right? 2 comma 7, or 2 times 7.5, 2 times 7.5, and 2 times 3.5. And when I calculate that, I get an area of 37. Now, 37 is between 40 and 28, a little bit closer to 40, okay? But again, I feel a little bit more balanced when I go and do this area, right? I've got some space that is over. I've got some space that is over and some space that is over. But that's a little bit balanced with this space that is under up here at the top in each of these cases and space that is under. So this feels like a better, maybe closer approximation. All right, finally, I'm going to go over trapezoidal sum. I'm going to come back up here to the top. And trapezoidal sums are a way to approximate area under a curve, just like Riemann sums. Riemann sums uses rectangles. Trapezoidal sum uses trapezoids. And both corners of the trapezoid are on the curve. So instead of just one point, you have 2 points. Again, a single trapezoid would be called a subinterval. We're looking at a function on a large interval a to b. I can approximate the area under the curve using n subintervals. Those n subintervals are again calculated by saying the difference in my endpoints of my large interval divided by the number of, in this case, trapezoids that we have, subintervals. And just as review, area of a trapezoid is 1/2 the sum of the bases, okay, times the height. We talked about the fact that the bases are the parallel sides and the height is the perpendicular distance between those. Okay, so we're going to go and do this example. Again, we're on the same interval, 2 to 8. And we're using 3 subintervals, okay? And so, again, 2 endpoints are going to be on my curve. And that's the big difference, other than the shape. That's the big difference between Riemann sum versus trapezoidal. Obviously the shape, but in this case I get 2 points on the curve, which might give me some more accuracy. Okay, and my delta x is still the same, right? 8 minus 2 divided by 3, and so 2. And so I can still get myself set up down here, right? Each are going to have a width of 2. I'm going to have 3 trapezoids sitting here. And when I go to draw these trapezoids, I'm going to draw it so that each endpoint or each corner of my trapezoid is on the curve. So I'm actually drawing up both sides here at the 2 and at the 4 so that I'm touching my curve at both sides. And then what I do is I draw a line connecting them, and now I have a trapezoid, right? Okay, so I'm going to stop right here. I'll draw more trapezoids in a minute, but I just want to label some things before we go and do that. Remember, if I'm going to find the area of a trapezoid, I have to do 1/2 the sum of the bases. Well, the bases are the two sides that are parallel to each other. These two sides here are parallel to each other. And so the base would be the height when x is 2. So it's like saying f of 2 plus, and then the height here. Well, the height is going to be the output of the function when x is 4, so f of 4. Again, I know that I can see that those outputs are 6 and 8, but I promise you that you will either not always be able to tell what those outputs are, or you will not be given a graph. Oftentimes you're given a table. We'll do more of that in the next lesson. So I want to get in the good habit of writing out what I'm calculating in order to get these bases, okay? And finally, the height is this distance down here. The height is actually the width of that subinterval, right? And so I've got times 2, because that's how wide my base is. I shouldn't say base. That's how wide the height is, or the delta x. All right, so I'm going to draw another trapezoid. Let's do this color. So again, I got to start here on this 4 and over here at the 6. I'm going to draw up until I touch my curve. Okay, in both of those spots. I'm going to connect those 2 points with a straight line. Now I have another trapezoid. Okay. And same idea. So I'm going to say plus, I'm going to run out of room, so I'll just do this vertically, plus. All right, well, this endpoint is f of 4. So notice that gets repeated from up above, plus the height when x is 6. Again, times 2, because that's the width of the space down here. And finally, let's do this next trapezoid. And this next trapezoid here is at 6. That goes up until I touch the curve. And then this gets strange again because, at 8, my function is on the x-axis. And so what actually gets drawn technically here is a triangle. But we're still going to count it as a trapezoid since we're working in that world right now. And so again, the base 1 would be the output when x is 6, plus base 2 would be the output when x is 8, just building good habits with the height of 2. So that, when I can't see the outputs, I know my setup. And I'm going to do this calculation, and when I type all this in, I should get 34. Now, if you notice, there's no overage here, okay? I'm not over by anything. In fact, all of these calculations are under. So we got a little bit of under, a little bit of under. Man, maybe the tiniest sliver of under, if at all possible, okay? Which means, my real answer is probably, my real area is probably somewhere between 34 and 37. When finding the area. So midpoint Riemann sum might be the most accurate way of calculating the area. Trapezoidal sum is also a very accurate way of calculating area, versus a left or a right kind of leaves me wondering how close I really am to my approximation. Okay, so your job is to complete the rest of this document by doing this problem here and doing the next page. Determine the width of each subinterval, assuming they are of equal length, and sketch each rectangular approximation. And so when you're doing this, you are looking at the type of Riemann sum it is, or not Riemann sum. You are looking at the interval that is given and how many subintervals. Okay, so you're going to do your calculation for delta x. And then once you do that calculation, you're going to come along here and you're going to draw those rectangles in. You don't know what the function is. There's no calculation to do. You're just practicing finding the subinterval width and drawing in rectangles. Okay, you're going to do that for 2A, B. On the next page, C and, I should say D, C and D. Okay, and then you're going to do problem 3. It says approximate the area under the curve using the indicated Riemann sum and the given interval and subintervals of equal length. Include a sketch means that I want you to draw in the, I'm just going to say subintervals. So obviously the graphs are already here, but just like we did up top, just like we drew in these trapezoids and rectangles up top, and just like what you're going to practice in problem 2, I want you to do the same thing in problem 3. I want you to draw in the rectangles or draw in the trapezoids, and then you're going to use the function. So I would use the y equals in your graphing calculator and the table feature so that you can calculate what those areas would be. And then be ready to go over this with me when I see you in class. Good luck.